time to do some practice involving multivariable integration, and we're going to be doing lots of practice. And where we're starting right now is the really basic stuff, because you want to start from the ground up. Make sure you can do the simple problems, and of course we're going to start adding layer upon layer. By the end, we'll be doing some amazing integrals. It's going to be fantastic. Now, as we do the practice, it's important that you do as much as you can on your own. So if you see a problem, pause the video. Try it yourself first. And then if you do need help, you can unpause and we can compare and talk about what's going on. The more that you do, the better you're going to get. I mean, we want to make sure you're the best. All right, let's begin. Our first problem. So let R be the region where x goes from 0 to 2, y goes from 1 to 4, and sometimes in interval notation, okay, the square bracket, 0 to 2, cross 1 to 4. We can even sketch that region. It's not really a hard region to sketch. So, okay, x is going from 0 to 2, y goes from 1 up to 4, and so we get a nice little rectangle. All right, so there's our region. And now our question becomes, if we know that the integral over our region of our function is 7, now we don't know what the function is. We're just told that the integral of our function is 7. Find the integral over our region of 3 times our function minus 4. Okay, now this doesn't sound like it's a hard problem. Of course, it's not. I mean, we're starting easy, but of course, don't worry. We'll do some challenging ones sooner or later, right? So what are we being tested on here? In some sense, what we're trying to test on is, do we understand the rules for integration? One of the most important rules for integration is our ability to sort of pull things apart, and the idea that integrals are what we would call, the fancy phrase for it is linear. And what that really means when we talk about linear is it works well with addition and multiplying by a constant, so our scalar multiplication. So we're going to pull this integral apart. All right, well, what does that mean? Well, that says, look, this integral over our region of 3 f of xy minus 4 dA can be written as, so we're going to break up over the minus sign. Minus is really just addition with, a negative factor pulled in. So if we did this in a couple of steps, I say, look, that's the integral over our region, 3 f of xy dA minus the integral over our region of 4 dA. Well, pull out the constants. Okay, so this would be 3 integral over our region of f of xy dA minus 4 integral over our region of dA. Well, good news. We know what the integral over our region is of our function. So this first bit is equal to 7. How about this second bit? Well, it's the integral over our region of dA. And what is that finding? Well, it says you're breaking things up, because that's what integration is, and the contribution from each piece is the area of the piece. Then you put it all back together, you get the total area. So if we look here, it's a 2 by 3 rectangle. So that says 2 by 3, the integral is 6. So we end up with 3 times 7, 21, minus 4 times 6, 24, which is negative 3. Now you might ask the question, are we allowed to have a negative value? And the answer is yes. I mean, without other information, integrals can be negative. You're allowed to have negative values. Now, depending on the context, though, you might be a little bit suspicious. If we were told, oh, this is computing a volume, we'd be like, oh, that's not looking good. But without other information, yes, integrals can take on any value we want because it's a total, and totals can be negative. You can owe money just as much as you can have money. All right, so there we go. Oh, that's a nice warm-up problem. Don't worry, more fun problems to come. Okay, our next problem. So, a lot here. So suppose we have some notation here. We say the integral, and there's this AB cross CD, f of x, y, dA, denote the integral of the function over the region a less than or equal to x less than or equal to b, and c less than or equal to y less than or equal to d. Okay, so in other words, it's a rectangle where we go from a to b in the x direction, c to d in the y direction. All right, that's not so bad. What are we after? Well, it says find the integral over a particular rectangle given that we have the following. And there's, looks like 4 pieces. So, maybe it's not so clear what's going on right now. But let's draw some pictures and see what we can do. Okay, so let's see. So it looks like, well, we'll have, we don't go very large in any direction, so we'll just mark here, 0, 1, 2, 0, 1, 2, 3. Now, what are we after? We're after 2, 3 cross 0, 1. Well, that says x is going from 2 to 3, and y is going from 0 to 1. So in other words, we're trying to understand what's happening in this little piece here. So we don't know. We're trying to figure that out. If we can figure that out, life is good. All right, well, let's mark what we do know. And we'll go through bit by bit. We can say 0, 1 to 0, 2. So that says x goes from 0 to 1, y goes from 0 to 2. Oh, we can fit that into a picture here. Well, that's, to be safe, we're going to mark all of these here. Okay, so we would have 0, 1, 0, 2. So that piece right there is worth 4. 0, 2, 0, 1. So that says now x is going from 0 to 2, and y goes 0 to 1. Okay, so let's see, what would that look like? So we'll mark off. Okay, so x goes from 0 to 2, y goes 0 to 1, is this piece right there. And that's worth -2. When I say it's worth -2, that's the total value of the integral over that part. All right, well, 2 to go. 0, 3, 1, 2. Okay. So x goes from 0 to 3, y goes 1 to 2. Actually, that says it goes pretty far in the x direction, but it's sort of up. So 0 to 3 for x, 1 to 2 for y is up here, and that is 3. Okay, one more to go. And the last part is 1, 3, and 0, 2. Okay, so 1, 3, 0, 2. Okay, so x is going from 1 to 3, and y is going 0 to 2. Oh, actually, it's kind of a big piece to finish up with. That's all right. No problem. No problem. So it's this whole piece here, and that gets us to 7. All right, now, what we have is we have all these little pieces, and what we want to do is say, let's look at ways we could combine. Can we put these together in nice ways? And notice, it looks like these two, the second and the fifth one, if we put those together, what do we end up with? Well, they fit nicely together, and they form an entire rectangle. And so we see, okay, we see that there's this one piece here, which has 4, and then there's another piece, which has 7. Great. So now, that says, look, I know how to do the whole rectangle. On the other hand, if we stare at the other 3 pieces, we say, whoa, look at these 3 pieces. So, in other words, those 3 pieces combine together, and what do we end up with? Well, We have, of course, the thing that we don't know. That's fine. I mean, if we knew it, we wouldn't still be talking about our problem. Then we have the part on the top, okay? And so that is a contribution of 3. And then we have this part over here is just negative 2. Now, notice the key thing here. In both settings, we're covering the entire rectangle. It's all there. And so the thing is, the total when we combine all things together should be the same. In other words, if I want to know the integral over the whole rectangle, I can add up over the pieces. So here I'd have 3 plus negative 2 plus the part I don't know has to match 4 and 7. Because in both cases, when we put the pieces together, we form the same shape. All right, well that says 1 plus something equals 11. So our conclusion is that the thing that we're looking for is 10. So it turns out, wow, this piece, there's a lot of weight there. You know, it's pretty heavy. That's okay. You know, that's fine that it's a large number in comparison to some of these others. It sometimes works out that way. But there we go. So this is kind of a fun, like, can we see how to fit all the pieces together? Now, of course, one of the things you might say is, well, how did we know we were going to fit the pieces at all? And so that's a great question. And I think sort of the clue as to what's going on in this problem is to sort of say, sketch the regions that are given. So when you're solving a problem, you always want to say, let me start with what's given. And when we see it here abstractly, it's not so clear. But when we see a picture, we're like, oh, I can see that things can start to form together. And it's that sort of notion like, oh, we can combine things. That's what gives us power and ability to make progress. So, all right. Well, I like this problem. So many good problems. So many good problems. Okay. So let's try more problems. Our next one. Find the integral 0 to 1, integral 0 to 2 of y over 1 plus x squared times dy times dx. Okay, great. So this is a chance for us to practice iterated integration. And when it comes to actually computing integrals, the majority of the time, we're going to be doing iterated integration. And what does that mean? Well, you integrate one variable at a time. So the way to see this is you should really say, okay, you work one layer at a time. You work from the inside out. All right, so we say, okay, starting with the inside, so the integral from 0 to 1 is still there. We're integrating with respect to y, which means that the x downstairs is being treated like a constant. So we can even remind ourselves of that, right? It says 1 over 1 plus x squared, that constant. And then when we integrate y, we'll get 1/2 y squared. Evaluate. Now, here's my suggestion to help keep track of evaluation. Because you have multiple variables in place, you want to make sure that when you're evaluating, that you're evaluating the right variable at the right time. So one way to do that is to, instead of putting 0 to 2 here, because then you're like, wait, do I put the 0 in for the x or the 0 for the y? You can say, look, I know I'm integrating with respect to y. This is really y equals 0 to y equals 2. So just to emphasize, so I can keep track and not make mistakes, or at least make fewer, you know, that's a worthy goal. The road to wisdom. It's plain and simple to express. Err and err and err again, but less and less and less. That's a poem by Piet Hein. All right, well, let's clean this up. Well, plug in y equals 0, you'll get 0. Plug in 2. 2 squared times 1/2 is 2. So we end up with 2 over 1 plus x squared. Say, all right, great. Now it's just single variable integration, kind of thing that we've done before. So this is 2 arctangent of x, because we know this integral. Oh yeah, we know this one. It's a great integral. Evaluate from 0 to 1. Arctangent of 1 is pi over 4 times by 2 gives us pi over 2. Arctangent of 0 is 0. Now, you might have said, wait, Steve, hold on. I like your answer, don't get me wrong, Steve, but why? Why did you emphasize so much y equals 0 to y equals 2? Why didn't you say, oh, this is x equals 0 to x equals 1? And the answer is, I absolutely could have, and it's not even a bad thing to get into the habit of doing. But at this stage, the reason I didn't worry about it here, but I did worry about it there, was there's no ambiguity. We were down to just one variable in play. It was up here where it was like, well, which variable are you talking about? When there's ambiguity, you want to say, okay, let me respect the notation and use the notation which is going to be the most likely that I don't get confused. So that's why I didn't put down the x equals down here. I probably should have. You're right. Good catch. Good catch. Well, keep going, right? More to do. More to do. Lots of fun problems left for us to try. Our next one. Let R be the region where x goes 0 to 2 and y goes 0 to 2. Find the integral over our region of x e to the xy dA. Okay, so we're going to find an integral, which means we're going to do iterated integration. Now you might say, how do you know that? Because that's the only way we find integrals is iterated integration. That's how I know that. Okay, technically, there are some times when we can interpret the integral, but that's not really finding the integral. It's just saying, aha, I know what the integral interprets as. We'll see examples later on. But essentially, if you ever see a problem that says find, we're doing iterated integration. And you might notice something. They didn't tell us how to iterate, because there's choices. If you think about what we have, we can sketch our region. It's a nice little 2 by 2 square. X goes 0 to 2, y goes from 0 to 2. So, okay, great. So there's really two possibilities. And let's think about what they are. Okay, so we could do integral 0 to 2, 0 to 2 of x e to the xy. And then we could say dx dy. Now, this one, if you're integrating dx dy, the way you should think about that is you're slicing, in some sense, in that method. Okay, so this is a horizontal slicing. We'll talk more about that in another session. The other way we could have done this is we could say, okay, look, that's 0 to 2, 0 to 2 of x e to the xy dy dx. And all right, well, what does that correspond with? Now that one is corresponding with what I would like to call vertical slicing. Now, which one is best? The answer depends on the problem. I would say that this is really a discussion we're going to have in another session, but I guess I will foreshadow the discussion because we'll say it again. If you don't have any other preference, probably dy dx is the way to go. And there's reasons for that, but we'll talk about them when we get there. But let's do both, right? Because if we do both, we should get the same answer, right? Okay, well, yes, I will tell you that I don't want you to think like, oh, something really mysterious is going on. This is not some exotic function. There's no part where there's something blowing up. Nothing crazy. But I want to compare and contrast. Okay. So let's start with the first one listed. Integrate dx dy. Now, if you were going to integrate this function, what technique would you need? Well, you need to do parts, because you have x e to the xy. There's two x's. They're multiplying together. All right, so let's come to the side here. The integral of x e to the xy. Well, okay, you let the x be the u, e to the xy be your dv, du would be dx, v, well, that would be, whoops, I forgot my dx here, integral of e to the xy with respect to x. Because remember, we're working with respect to x. Keep track of it. That notation is really key now. It tells you what you're integrating with respect to. It would be e to the xy, but then you have to divide to compensate for the fact that there's this y upstairs. So there's a 1 over y. Okay, so you end up with uv x over y e to the xy minus the integral of v to u minus integral 1 over y e to the xy dx. Okay, so that's x over y e to the xy minus, here, 1 over y squared e to the xy plus c. Okay, so we get this is equal to, all right, integral 0 to 2, that's the outer layer. And now we integrate the inner layer. Okay, so that's x over y e to the xy minus 1 over y squared e to the xy. Evaluate that from x equals 0 to x equals 2 and dy. Okay, well that would be integral 0 to 2, plug in x equals 2. What do we see? Well, we're going to get 2 over y e to the 2y. Then we're going to get minus 1 over y squared e to the 2y. And then subtract, plug in 0. Well, the good news is when you plug 0 into there, you get 0. There, you don't get 0, right? You get e to the 0, which is 1. We're subtracting that, so it's going to be a plus 1 over y squared. All right, and now you look at that and say, cool, how do you integrate that? And the answer is, we don't want to integrate this. Oh my goodness, oh wow. This is not looking promising. Yeah, this is something we don't want to integrate. We can't find antiderivatives for some of these expressions. Now, 1 over y squared, that's easy enough. And you might say, hey, that looks like it's blowing up to infinity, but you have to be careful that when you put all of these together, it might just be enough so that it actually does not blow up to infinity. And it turns out that it won't. But you can see, okay, this at this stage we'll say ugh, which is a technical term saying we don't want to keep going. And really, more to the point, we can't. We can't keep going. We're stuck. But remember, there were two options. So now let's go to our other option. When we integrate in the other order, dy dx, what do you see? Well, how many y's are there? One y. So when we integrate, well, what will happen? We'll get integral 0 to 2. It'll be e to the xy. Then you have to divide by x, but there's already an x there. So it becomes simply e to the xy. Evaluate that from y equals 0 to y equals 2. All right, wonderful. Well, we can carry that evaluation out. All right, so this would be the integral 0 to 2 of e to the 2x, subtract e to the 0 times x. Well, that's e to the 0, which is 1. All right, well, that we can also compute. That's 1/2 e to the 2x minus x. And evaluate x equals 0 to x equals 2. And, okay, plug things in. We're going to get 1/2 e to the 2 times 2. So that's 1/2 e to the 4. And then minus 2. Great. Subtract. Plug in 0. E to the 0 is 1. Don't forget that. So 1/2 minus 0. Or we can say this is 1/2 e to the 4th. And minus 2 minus 1/2 is minus 5/2. And we succeeded. No problems. In fact, we could almost say this was kind of pleasant. And it's amazing because it doesn't look like a crazy function, but yet we see by changing the order of integration, we say, in one way we get completely stumped, and the other way we get an answer. Now, it will often be the case that in both ways you'll get an answer. I don't want you to say, oh my gosh, there's only one way, and I better get it right the first time. But I do want to say, hey, be open to the possibility, the idea that, look, maybe you should change your order because things can get hard. And if something gets hard, go back and consider a different order. And there's kind of a clue that we should have started with dy dx first. What's the clue? Think about the first step. So you could have said, look, I could either integrate with respect to x first or with respect to y first. And we look and we say, hey, if we integrate with respect to x first, two x's, that looks like we're going to have to do parts. But if we integrate with respect to y, it's like, there's only one y. That looks pretty straightforward. So if you just think about what would be the first kind of integral you'd like, that often helps you say, how do I get started? All right, cool. Good problem, good problem. By the way, it turns out if you integrate that, if you could, that's what it would be. Because look, it's the same integral. It's the same function over the same region. So how do you get from this integral to there? Good luck. I don't think I could do it. It'd be tough. Well, there are things that you could do, but it would not be fun things to do. So we won't do them. All right, but we will do more problems, right? Yeah, of course we'll do more problems. It's always good to do more problems. Find the volume between the surface z equals xy squared and the xy plane for the region R is 1, 3 cross 0, 3. Okay, so this is just saying, look, we're having x goes from 1 to 3 and y goes from 0 to 3. Okay, so 1, 3, 0, 3. We're doing rectangles. We will get to non-rectangles eventually. Don't worry. Not every problem that we'll ever do is a rectangle. There's going to be some fun stuff when we start doing non-rectangles. I'm looking forward to the day. So, well, where to begin? Now the question is, how do you do volume? Well, if we think about volume, we say, let's break our things into little parts, find the volume of each part, because of course that's how we do things, is understand what's happening with each part, and we put it all back together. Okay, and in particular, one way we can think of it is if we have some surface. So here's sort of a three-dimensional picture. I'm not claiming this is the right picture for this particular problem, but we have this surface upstairs and doing something. And what we can think of doing is we say, look, let's split our volume up into little pieces. So it's like, okay, here's a little tiny piece downstairs, and we come up to the part upstairs, and we're like, great. So I just need to understand what's the contribution of that one part. So the way we can do it is we can say, okay, volume, it's the integral over our region of height times dA, right? Because if you think about it, think about how we think of integration. We're breaking things into little pieces and saying what's happening with each piece. Well, each piece we get a contribution, a height times an area. So this is the volume of the little piece, added up all the little volumes to get the total volume. Well, for our case, we're like, fantastic. Integral over our region, and then our height is the surface, because we're going from the surface down to the plane. So that height is just the difference. Well, the plane, this is secretly another way of saying z equals 0. So the integral xy squared dA. All right, well, great. What happens? Well, we have to choose, right? Now we could do integration in both orders, but I think for our purposes, I think we're pretty confident that if we can find one answer, we'll be happy. And so for us, well, since it doesn't matter, let's say 1 to 3, that's our x. 0 to 3, that's our y. And then we're going to get x, y squared, dy, dx. All right, so, work through one layer at a time. So, integral 1 to 3 of, we integrate with respect to y, x is a constant, so we get x times 1/3 y cubed. Evaluate that, y equals 0 to y equals 3. And we're going to dx. Okay, so before we do our next integration, we need to evaluate. When we plug in 0, we get 0. Woohoo! Nice. When we plug in 3 cubed times 1/3, well, you can cancel one of the 3, so it really becomes 3 squared, or 9. So we say, okay, this is integral 1 to 3 of 9x. Well, that's an integral we can do. What is that? Well, that's 9/2 x squared. And evaluate here. Well, no ambiguity, so 1 to 3. So that's going to be 9/2. And then plug in x equals 3. 3 squared is 9. 1 squared is 1. 9 minus 1 is 8. 8 times 9 over 2 would be, really it's the same as 9 times 4, which makes it 36. And we're done. Pretty straightforward. Aha! Wow, our first application, volume. But in some sense, it's really a simple application because that's how we oftentimes think of integration. When we think of Riemann sums, we think of, ooh, let's make things like little pieces of volume and add them all together. So, all right, good. The first of many volume problems that we will likely be doing. Okay, well, let's try another problem. All right, so find the integral -5 to 5 of the integral 6 to 27, arctangent y to the 6, sine of x to the 53rd, dy dx. Oh my goodness, wow. Okay. Okay, this is not looking too promising right now, is it? We got to think about this one. Okay, so when we look at this, we say, okay, right now we have to integrate arctangent y to the 6. So if we take it as written, we'd have arctangent of y to the 6 dy. The sine of x to the 53rd with respect to y is like a constant. And so we think, oh, that's not looking too promising. Arctangent y to the 6? I don't know if we could integrate that. I mean, we could make a little bit of progress doing parts, but I think we'd get stuck pretty quickly there. But the nice thing, of course, is we have options, right? We can change the order of integration. Now, the nice part here is it's super easy when you have a rectangle. Now, how do you know you have a rectangle? So a rectangle, and of course you might say, well, that's the only thing we know how to do right now. So rectangle really says all bounds are numbers. That's how we think about a rectangle. And I'm going to put rectangle in quotes, foreshadowing something coming up. But we should think of a rectangle when all bounds numbers. And in that case, it's super easy to switch order of integration because you have choices. If you say, look, if you don't like the order that's given, change it, and maybe you'll like that. So let's see. If we did change our order of integration, so that would be now 6 to 27, -5 to 5, and then we get the arctangent of y to the 6, sine of x to the 53rd, dx dy. All right, great. So now, instead of having to integrate arctangent of y to the 6, which is crazy, we just have to integrate sine of x to the 53rd, which is also crazy. Oh my gosh. Oh, what are we going to do? Both of these functions are really unusual functions, but I will say, looking at them, this sine of x to the 53rd strikes me as a kind of a peculiar function. Very strange, unusual. Not the kind of function you might see walking around every day. Some people might even say that that function is odd. This is an odd function. Now, there's probably one of two reactions. Whoa, cool is one reaction. The other reaction is like, eh. I guess the third reaction is, what do you mean? It's odd. You said it was strange. Okay, so what does an odd function mean? An odd function says if you plug a negative value in for x, the output will be the same as if you had plugged in the corresponding positive value but just changed the sign. In other words, f of negative x is negative f of x. That's what we mean by an odd function. Okay, so you can check. Sine is an odd function, and if you plug in negative x to the 53rd, well, that's the same as just a negative times the x to the 53rd, and then you can pull the negative all the way out. Okay, so how does that help us? Well, notice something about these bounds. Very suspicious. See, the 6 to 27, hopeless, hopeless. But negative 5 to 5, those are nice in that they're equally around 0. Okay, so how does this all fit together? Well, it turns out that if you have an odd function and you integrate from negative a to positive a, you can see that the areas will cancel out. So that the integral from negative 5 to positive 5 of this sine of x to the 53rd, and this arctangent y to the 6, we can really think of it as, for the time being, acting like a constant since it's with respect to x. So we say, aha, use symmetry. Well, we had to switch the order of integration to get there. Notice that our original function, arctangent y to the 6, it's not an odd function. And the bounds were terrible. And so we weren't able to use anything about symmetry to simplify. But after we switch, we say, aha. So by symmetry, this is the key idea here, we say even though we can't actually find the antiderivative, we know that at the end, the total contribution will be 0. So that says this integral on the inside, this inner integral, is 0. So this becomes the integral 6 to 27 of 0 dy, which, that's easy to compute, that integral will be 0. Now you might say, Steve, shouldn't you have said it's 0 evaluated from 6 to 27? Yeah, but it's still 0. Okay, so done. Done. All right. Another, hey, sometimes it helps to switch order of integration, but also don't forget all the fun things we learned in Calculus 1. Things like symmetry. Symmetry is your friend. You should hang out with symmetry more often. Invite him over for dinner and say, hey, symmetry, it's been a while. Why don't you come on over? Bring the family. Let's have a talk. All right. One last problem to finish it up. Here we go. Find the following. Integral from 0 to pi, integral 0 to log of 2, sine of x e to the y, minus y sine of x, dy dx. And I'm just going to tell you at the beginning, there's no secret trick here. That's not what this problem is about. I want to take this time to talk about a certain, I don't want to call it necessarily a technique, but there's a certain approach you can use to problems of this type. Now I want to be clear what I mean of this type. So notice our function, we could rewrite this in the form sine of x, because that's common, so I could factor it out, times e to the y minus y. So in other words, some function of x times some function of y. And simultaneously, we have a rectangle. And here, rectangle just means all the bounds are constants. That's what, when I say rectangle, that's what I mean. Well, when that's the case, here's the fun thing. You are allowed to, instead of doing the integrals sort of sequentially, in other words, do one layer, do the next layer, you can do them parallel. You can do them both at the same time. So in some cases, it makes the computation a little bit faster. So it says, oh, instead of having a couple of lines, I'll just do it in one line. So let me be clear what I mean by this. What happens is it says, okay, you can pull part of the integral that involves x into one thing. So what's the part of the integral that involves x? There's the dx, that's attached to the integral from 0 to pi, and that's attached to the sine of x. So integral 0 to pi of sine of x dx. And then, simultaneous, you say, okay, grab all the integral that's with respect to y. All right, what's that? Well, there's the dy, the function of y, and then you got your bounds of y. So, integral 0 to log of 2 of e to the y minus y dy. So, what can we do now? Well, the answer is just do the integrals. Okay, so we get the following. Integral of sine, negative cosine, and evaluate 0 to pi. It's just a single variable integral. We don't need to specify. Integral of e to the y minus y, e to the y minus a half y squared. And evaluate 0 to log 2. Okay. Now, again, I'm just doing things simultaneously, right? Parallel just means they're going on at the same time. Sequential says do this, so we do, then do the next one, do. So that's the difference, right? Sequential versus. I sound like I'm trying to be a programmer and saying, oh, sequential versus parallel. But the moral is you plug things in. So cosine of pi is minus 1. Minus 1 makes this a positive 1. Then we're going to subtract minus cosine of 0, minus 1. And here we have e to the log of 2, 2 minus a half, log of 2 squared. And then subtract, plug in 0, e to the 0 is 1 minus 0. So, leaving us with 1 plus 1, which is 2, from the first piece, times, here, 2 minus 1 is 1 minus a half, log of 2 squared. And we're done. That's it. That's the integral. So, when you have the situation, and I really want you to be careful here, because I don't want you to overuse this, or more importantly, misuse this. You have to have a couple of things. You have to have a rectangle, which means all your bounds have to be constants. And we will see that there are cases when that's not the case. So make sure you have that. And your function has to be the case where you can write it as a product with the different variables. So there's some function of x times some function of y. Or whatever your variables are. You know, your variables don't have to just be x and y. You can have your variables be whatever you want them to be. When that's the case, pull your integral apart and just run the pieces individually. It can be a little bit faster, and it can sometimes be easier to keep track of what's going on. So that's just a nice option that you have, and keep that in mind. One side note, you might say, hey, can't we pull down this too? Right, because of products of logs? No, you can't. Be careful. Make sure that when you're applying properties of logs, not products, properties, that you're applying them correctly. See, this 2 is outside of the log. The log is being squared. If the 2 is inside the log, yes, it comes down. Since the exponent 2 is outside, it does not. All right, well, a great way for us to finish our start into multivariable integration. Many more fun integration problems still to come. Looking forward to it and hope to see you back again. Bye.